after the talk, there will be an informal discussion of the formal abstracts project. So if you're interested in that, stick around.
Can I briefly say something about it?
Yeah, please do.
Okay, so basically, Tom has this formal abstract project, and Joseph has the idea that we should collect examples of things that would be hard to do in this framework. So he decided we will have a meeting with people to suggest difficult examples. And it will start 5 minutes after this talk ends. So please, as many people, please come so we have some input. That it's not just me, Joseph, and Tom.
I'll be there. So I've been practicing Ekaterina Komendantskaya. Did her dissertation work in Cork, Ireland. After that, she was sucked in by the Coq community, so she worked with E.McLean in Sofia, INRIA, Sofia, and Tripolis. And then she's been in various places in Scotland, but now she's at Heriot-Watt. Yeah, so far so good.
Yes, excellent.
Yes.
Thank you.
And her dissertation work was on this interesting bit of trivia, was on logic programming and neural networks. And so even though that's not exactly what she's doing now, it informs the work that she's doing now. So, no meeting on big proof would be complete without some big data, a little bit of big data, or at least machine learning. And so that's what she's going to tell us about.
Yeah, well, thanks a lot for inviting me to, first of all, to be in the audience. It was a huge pleasure to be in the audience and to hear all those great talks. And thanks for inviting me to speak as well. So when I was invited, I thought hard why I was invited to speak, and then I figured out that it must be because of my work on machine learning for Coq and ACL2 that I have done. So I hope I guessed right. And this is what I prepared. So all these are my co-authors in this field: G.Grov, T.Gransden J.Heras, M.Johansson, E.McLean, and N.Walkinshaw. There will be parts of the talk that will be about work with them, in which case I will clearly signpost that. So my experience with this machine learning for ITP topic goes back to 2012-14, when we had like a pilot project, really playing with it and trying to see what we could do for proof general and Coq and its dialect process effect there. Then we did like a spin-off project in ACL2. It was funded by SIX, an industrial project. And then I just had a little collaboration with some other people working in the UK on this topic. So when I thought about this talk, I thought actually the interesting question is not what I think about machine learning for interactive proving, but what you think about it. Because that was the question that was arising again and again in all these years, because the topic is about tools, right? And when you're talking about tools, then you're talking about what kind of audience the tool will have, what kind of users it's going to have. So whenever we try to do something, obviously that question was the main one, and then everything else was following. So I think the best thing would have been to just stop here and ask you what you're thinking. But on the other hand, you may tell me, well, it's difficult to say what we want until you show us what we may want. Yeah. So people never wanted Facebook until they were given Facebook. So let's regard this topic really about what you want, but I'll tell you about these 3 projects as an example of what you might want to want, yeah? But you don't have to want those things. It's just it was our best guess. And so at the end, it would be nice to hear your opinions about what you actually want. So what is statistical machine learning for interactive proving, and why we care? And we care because we know that in principle we cannot automate everything that we do in interactive provers. The logic is just too rich, too expressive, so there will always be those areas which are not automated. And then we think, well, maybe we can have some assistant where we cannot have deterministic algorithms deciding certain things for us. Maybe we can have a bit of a help from machine learning. And well, the first refinement of the question, what statistical machine learning for ITP would be, well, it's about assisting the human user in completing his or her proof. And this was the perspective that I really like to take in all of my work. But many people also ask that question in a different way. In particular, Joseph Urban has done a lot on machine learning for better automation. How can we use machine learning in order to improve automation where it would get stuck? Otherwise, maybe machine learning could guide, say, the choice of lemmas or such things. So we'll be really going back and forth these two questions, but I guess my preference is actually the first topic. But we will see. We'll see a bit of both. So it might help to think about this in terms of, okay, so we have our provers, we have interfaces for interactive provers. There was a slogan, definitely in Britain, about environmentally friendly policies. It was reduce, reuse, recycle. So we may think of trying to revisit, reuse, recycle our proofs as a way to be more environmentally friendly in our proving environments in order to save our time. So that's the analogy. So how to revisit existing proof libraries is the question how we can mine interesting proof patterns. Yes, it's simply revisiting. It's not really reusing them, automation. It's just sort of what kind of similarities are there in my proofs? Could you help me to find that my proof is similar to, I don't know, someone very clever? The second question, how to reuse. So this is more about automation. Maybe someone else has already proven that, and maybe I can recombine his or her strategies and get my proof going. And if reuse is too simplistic, and which it often is, because if everything was solved by the combination of existing tactics, it would be too easy, and this meeting wouldn't have probably even happened. So maybe we should be talking about recycling. Maybe there is some kind of high-level strategy that I could borrow, but not actually recombination of existing tactics. So I'll be going back and forwards within these three questions, because I think they're sort of at least drawing some kind of field where one could ask questions. So when we started this, my research assistant Jonathan Harris and I, we basically sat at some point and said, okay, what would we have liked ourselves in Proof General when we work with Coq files? And both of us said, well, actually, sometimes you're in the middle of a proof, you don't really know how to finish it, but you feel that you've seen that, you've done this before in some way, obviously not in this notation, not with these particular types, but kind of in a similar situation, this proof has been somewhere before, but you can't remember in which library, when it happened. Maybe it happened 2 years ago, 3 years ago. So how about we'll try the machine learning tools to do this kind of recommender for us, saying, hey, by looking at all libraries, your proof looks a bit like this one. So, and then how to do this? On the engineering side, Proof General at that stage, and I think still is one of the most popular user interfaces for Coq at least, and we were going to work with Coq because we both knew it and had some experience with it. So so the top level is what happens in Proof General and Coq anyway. So there is the user. The user has this interface where that person enters his lemma theorems and sometimes uses static language to have the proof completed. And then this interface contacts is integrated with Coq, Isabelle, ACL2, whatever prover you can imagine. And then whatever proof you type in here gets sent to the actual Coq engine for type checking, type inference, and so on. It's easy to imagine that this user interface is also connected with some machine learning tool. So when you're doing your proofs here, this bottom leg of the process is watching you somehow, gather statistics behind what you're doing, and then if you want to call it, you just call it and it will give you back some suggestions. So that was like an engineering framework that we're playing with. And it seemed easy enough, so the user can't be bothered with calling this, the user just doesn't call it, and if, once in a week he wants to call something and find some similarities in proofs, good. Okay, so that's the deal. Instruction, and we call this little extension ML4PG, machine learning for Proof General. Although we should have called it machine learning for Coq, really, because we didn't work with all these interfaces. But I guess as an engineering solution, it's just, you know, machine learning for proof general. You could imagine this being extended to other provers as well. So one interacts with proof general in any way that person wants. That person gets stuck in a proof, calls them L4PG, command line or a button. It's quite easy to implement this in proof general. And then an L4PG tells me that there exists 3, 4, 5 lemmas that seem to be similar to mine. So for those who haven't worked with Coq, I think most actually of the audience have, but just in case you haven't, we're going to look at just the interface. This example of little lemma trying to prove tail recursive equivalence of tail recursive and recursive implementation of factorial is not very important at the moment. Let's just have a look at the interface. So you're usually working in one window, and another window is like a response that Coq gives you in response to the taxes that you type. So this is the user, just entered this lemma. This lemma will self-check that it's syntactically correct and so on. And then that person uses some tactic. So this is an SS-reflect dialect of Coq. Some tactic, again, let's just for now not worry too much what tactic it is. But in response to the tactic, the current state changes. And then elimination, so move M is just eliminated one of the quantifiers there. Then elim is an induction step, and so the proof split into base case and inductive step. And then the base case was discharged by this tactic, and then we have inductive case to prove. So imagine that base case was really trivial, and I did it quickly. But then I couldn't really make up what to do next with the inductive case. Well, I could just press a button or on the command line, and I would like to have something like this. So look, your lemma is similar to other lemmas, and as it happened, someone before me has already proven similar lemmas about recursive and tail recursive versions of other functions. And then if I actually go and expect those, I will see that their proofs follow pretty much the same strategy. So that's kind of on the user interface side what we imagined and what we implemented as a working prototype. What happens on this machine learning leg? So that's proof general. It interacts with Coq, and this is our MATLAB Weka. We tried a couple of different tools, but really, what kind of tool there was really didn't have much of variance on our work. So first of all, on this proof general level, we had a little script that was extracting features from proofs. Because whichever tool you take here, it expects some numerical vectors as input. So it doesn't want to see theorems, of course, but it wants some vectors of numbers. So there was some feature extraction implemented on top of here. It extracted features from terms and types, initially from tactics, but later on from terms and types. And we developed our own method of recurrent clustering to do this. After conclusions, I have a couple of slides. If the audience will be interested in this particular method, I'll tell a little bit more about it. But I think this was the only, recurrent clustering was the only really clever part of it. Well, the rest was really an engineering task. So we had this recurrent clustering method to actually gather the features because we didn't want to parse our terms and types literally. Yeah, you don't want to parse NAT as NAT, 3 letters. You want the tool to know that NAT is an inductive structure itself. So it's not the literal parsing of the files, but actually parsing of some recursive structure of them. So that was a clever part. Okay, so once we got all the features, we represented all our terms and types somehow as features. We would send it here, and this tool would just do whatever it likes. We asked it to do clustering of all the data we gave it. And then on the next stage, it would cluster it. It would say, okay, I have 200 clusters with these particular objects. And then these objects would be fed back as lemma names to the user, just in the way that you've seen. In the window, you'll say, well, your proof looks like these 3 lemmas. So the user actually never sees anything on the machine learning side. yeah, it kind of all happens under the hood. So we tried a few clustering algorithms, and the basic idea is this. If you only had two features, if I represented all of my proofs with just two features, all my proofs would be points in a two-dimensional space, and then a clustering algorithm, any of the existing, would just partition it into some clusters. Well, of course, we don't represent all our proofs by two features. It's about 100 of features for every proof that we use, in which case each of our proofs is a point in 100-dimensional space, so to say, for as far as the machine learning algorithm sees them. So this is what happens on the machine learning side. And we tried a few existing implementations of clustering algorithms, and they all performed approximately in the same way. Right. So this is the general setting. Are we all kind of happy? Any preliminary questions? Or? Yeah, well, okay. So let's have a look at one mathematical example which we like the most. I had a look at all the files. I think this one is always the prettiest. So we took three disjoint, or what we hope to be disjoint mathematical libraries in a SES-reflect library, to which George gave an excellent introduction to us this morning. So linear algebra, combinatorics, and this persistent homology, you may ask, what is it? It was a library that my research assistant Jonathan developed towards the end of his PhD. So we specifically chose it as something that's not a base library, because you think, well, base library is something that's written very uniformly, probably by the same set of authors. How about we take just something completely external to the base library? So, and there were a couple of libraries with just standard definitions and so on. Okay. And 758 lemmas theorems would translate into many more lines of code, because obviously there are definitions and notation and whatnot. Yeah, and then we chose some problematic lemma that we will imagine we struggle to prove. We imagined that we can complete very few basic steps, and then see what an alpha-PG could suggest to us. And part of this story would be a SES-reflect library with big operators, about which, again, George told us a little bit. So it allows you to write big sums, big products, and others in a nice way. So most of the examples you see in next few slides will be in that library, or using a notation from that library, rather. So let's have a look. So that was our imaginary case of problematic lemma that we cannot prove. So first of all, a definition. Let M be a square matrix, then M is nilpotent if there exists an N such that this formula holds. And now a statement of the theory. So if indeed M is a nilpotent matrix, then we have this property holding for where N is such that Mn equals 0. So, you know, we thought it's kind of probably not the most difficult theorem you're going to prove, but it's not as trivial as a version of factorial and stale recursive version. Right. So now let's do those imaginary few easy steps, which would any person who has ever used Coq or similar prover would do. So this table shows a few steps of instruction. So that's the statement of my lemma, but in a slightly nicer notation. So that's how the previous lemma would have looked in SES-reflect as raw, and I just prettify it a little bit so that it's easier to read. So first of all, if anyone sees, suppose I don't even understand what the statement is about, yeah? If I see implication and quantifiers, it's usually a signal for me that I want to take the left side of implication as a hypothesis and get rid of the quantifiers. This is even if I don't understand what it is even. So that's what move does for us. So those three things that it moves to the hypothesis space is quantification over two arguments and the implication. And so we are left with this statement. Then we do some rewriting. In order to simplify this formula, this is basically, we're distributing this multiplication into summation, and we get a simpler formula. So we're using, again, a few a few lemmas definitions there. When we're here, it's sensible to do some kind of induction on n, and that's what we're doing. So in this case, actually, full induction is not needed, so we're just doing case. And the case split, the first formula it gives to us would be for m0, and here's this the second case, inductive case for n plus 1 in that corner. And then again, imagine the base case was simple. I just used some basic facts, and then I just didn't know how to proceed because inductive case was somewhat harder. So these are the few steps that we done, and then we called our tool to see what it would suggest to us, if anything useful. And then this is what it suggested. So I have no idea what it is. It's Jonathan's file. It's about some persistent homology he was studying, and one wonders, is it a good suggestion? Maybe it's a complete bug. Well, suppose again I'm not really deep into what library about persistent homology is, but I can still run the Coq file and see what's actually going on with this lemma. And this is what's going on with this lemma. There is if I look at it, what actually happens in the proof in Jonathan's library, I will see that first of all there is distribution of this outer summation going on, and then some of these components are now cancelled pairwise. One and then two more. And then I'm just remaining with much smaller formula, and then absolutely same tactic repeats. Yeah, think of this as a kind of further strategy. Yeah, you have summations, you distribute them, and then you simplify. It's sort of how I should read these suggestions. There is a lemma, and here's kind of like a little method for you to try. Okay, and then the proof proceeds in the same fashion, so I won't repeat this again. That was suggestion number 1. Okay, and that was suggestion number 2. A much simpler fact and in a much closer library than persistent homology. And again, if we look at it, what happens? Again, there's distribution of summation, pairwise cancellation, and we're left with much smaller formula. So kind of same strategy. It's completely different libraries, and of course now I'm writing this all in a uniform notation, but all types and everything was different in these libraries. All notation was different. So actually the tool was able to learn all the notations that exist in different libraries. That's the proof strategy that as humans we would gather if we actually have a look at these suggestions. So we need to case on n, prove the base case, and then expand the summation, cancel term pairwise, and then we get just the first and the last term when we do this. So back to our example with which we started, our problematic lemma that we couldn't finish. Well, we could just follow absolutely the same strategy, expand the summation, and then cancel terms pairwise and get our result. So this was one of our favorite examples when we saw it. There was actually 3 suggestions, and this was the third. And you'd look at it and you think, no summations, So there must be a bug, because all other previous statements were about summations and expansion of summations, and this one is not. But actually, if one runs the proof, the summations come in the proof, and absolutely the same strategy repeats. So it was able even to find patterns beyond, the simple fact that, this is summation, that is summation. So, this particular lemma doesn't involve any summations. There is a formula with summation occurring in that proof at some point. So why did we like that example? Because it's kind of challenging, even for a human user. After a few steps that we have done, just resolving basic case and so on, to see that actually those 3 lemmas from absolutely different libraries on different notations are similar. if someone said, well, I could probably do this with blind keyword search and just started to search all lemmas that involve big summation, that person would have got 250 lemmas in the same libraries. So inspecting 250 lemmas is silly. You wouldn't go over every lemma within 250 to check if it applies, if it has any strategy that applies to you. Whereas 3-4 suggestions is something that you could do if you really wanted to. So we were really happy with it. We submitted it to ITP, and then we got a rejection. And we were just, now it sounds funny, but at that point we were just shocked. We thought now everyone will say, wow, it's amazing that you could do this. You know, no one else could do it before you, and you can. And obviously that was not the only example. We had lots of different examples, and we'll see a few today as well. So what reviewers didn't like in particular, well, first of all, Coq community doesn't like black box proving anyway, full stop. So, but this is what we were ready for. It's okay, we thought. But then we had a machine learning side of the audience, which was saying, so what's the evaluation really? Yeah. So first of all, how many theorems does it help to prove? And you see, the way I showed it to you, and that's how we intended it to work, it didn't actually prove for me my lemma automatically. I inspected those 3 proofs. I kind of myself as a human thought, oh, that's the strategy that they were all using. So why don't I use the same strategy? But the actual proof in Coq was in different notation, and you know, I wasn't copy-pasting proofs. I was trying to generalize it as a human being. So we couldn't say, oh, you know, this is how we proved 5 lemmas, because we proved, not the tool proved. And then also the question of, so how do you, so okay, your tool works, we believe you, we run it, fine, it gives me all the time some 5 lemmas. How should I judge if they're interesting? In this particular case, you were able to say, oh, that's the strategy, and this is a nice strategy, and it's a reusable strategy, but who would going to say it to the user every time that the clusters are shown? So we were completely heartbroken at that, because this was exactly what we did. So we wanted it to be a user tool rather than an automated tool. And obviously an option would be to gather 100 mathematicians and check whether they find the tool useful, but we were not very much into HCI solutions. So what to do? Well, we could try to maybe find evidence about this method in some other different ways. And since then, I tried to kind of use this method of recurrent clustering into other settings, basically as a way to convince myself that, or not convince myself, that it's actually an interesting method. So one opportunity came from J.Grov, who was working in ACL2, and he gave us the following task. He said, well, those of you who heard the talk by J.Grov, you remember a little bit about ACL2. But if you haven't, the best comparison with Coq is, imagine a prover with just 2 tactics. One is simplification, and the other is application of different lemmas. So if you're in ACL2, it's still an interactive prover, but the prover will ask you to provide a new auxiliary lemma to try. So when it's stuck, it still needs a user to do something, but the only thing the user can do is supply more lemmas for it to try. So he said that very often when he does industrial proving, many tasks are routine. So we never ever were talking about discovering new theorems with this. Yeah, we're always talking about kind of simplifying the life of the user. And he said, well, here's a good task. Very often there is a team of developers, and there are some experts who do proofs just on the fly. It takes them 15 minutes to do the whole proof. And others are new users, and they have no idea what kind of lemma they should supply. Their proof doesn't go through. They're kind of sitting there. If only they could know that there is an expert next door who has done a similar proof, and then they could analogize from this. So, and as an example of this industrial development, he said, well, maybe try Java Virtual Machine projects that they had. So the goal in the industrial project was to model a subset of GVM in ACL2, and then we tried this in Coq, so you will see a mixture of examples today. Define an interpreter for GVM programs, and then verify correctness of GVM programs within whatever you chose, ACL2 or Coq. And there is a nice paper by Jay with a co-author about this. Okay, so for example, if you're a new member of the team of Jay, you may be given this task to verify that factorial is computed correctly by the GVM. So that's your goal, is to prove that for every n, running the bytecode associated with the factorial program with n as input produces a state which contains n factorial on the top of the stack. That's an example. To prove this, you have to go through a methodology, and methodology is given to the whole of the team, to expert and non-expert. So the bullet points on the left, everyone knows, pretty much. You need to write specification of the function, and that's an example. So this interesting sign is just this s-reflex notation for factorial. Yeah, so it's not n prime. It's a notation for factorial. N factorial, that's how it should be read. Write specification. Write the algorithm. Well, the assumption is that in Java programs they're all tail recursive, or the closest one that you can implement to a Java program will be tail recursive rather than recursive. You prove that the algorithm satisfies the specification. Then you write the GVM program in your prover. So in this case it's in Coq, but you could do absolutely the same thing within ACL2. You define the function that schedules the program. I don't expect you to really understand the code, but it's kind of like a methodology, yeah. Define the function that is a scheduler, and prove that the code implements the algorithm. And finally, you prove the total correctness. So basically, that's your schedule doing some computations. That's the top of the stack, and the top of the stack should be equal to the n factorial as it's implemented in the prover. So it's not a tail recursive version, but the actual version as we know it, the recursive definition. So, automation could be, by analogy, kind of this help by analogy could come in every step where this proving happens, because doing this for factorial would be the same as doing this for exponent or power or many other functions that people would take to verify this way. So let's have a look at just this one. Prove that the algorithm satisfies the specification. So I'll switch now to ACL2 to give you a bit of a flavor, but sort of the example that I've taken is also published, and you can have a look if you're interested. So in ACL2, we try to use absolutely the same method. I won't go, you won't see too much of, if any, of ACL2 code in these slides, so as not to confuse you with two provers. But I'll explain you in general terms. So the user is sitting here, and there is interface of ACL2. So this is kind of a part of this design is borrowed from ML4PG for Coq. You have the same feature extraction using recurrent clustering. You do your clustering with some off-the-shelf machine learning tool, and then you send similar lemmas to the user. So this one arrow would be very much like ML4PG used to do. Just show someone what similar stuff there is in the library if someone calls for it. But also, we tried to actually see, can we reuse this stuff? And similar lemmas were also sent to a little other program that was trying to analogize the lemmas, auxiliary lemmas in particular, for this proof to go through automatically. Yeah, so this is about automation.
Was that an existing program?
Yeah. Meaning, oh, this interface, is it existing?
No,
so
the box here, the box, the one that you're pointing now.
Oh, no, this one we wrote for the sake of this paper.
Okay.
It's existing now. Yeah, so all of it was in principle implemented from scratch. All these bottom lines of the interface with ACL2 existed before. So the idea was this. So can we use the output of statistical side to help ACL2 to generate those missing lemmas that otherwise would have been needed, would have been provided manually? So think of your theorem that you cannot prove at the moment as target theorem. Yeah, that's what you want. Think of, in the same fashion, your machine learning algorithm telling you that, oh, there is actually a similar lemma already in the library, and we'll call it source theorem, source lemma. But this source theorem, as per ACL2 fashion of proving, well, its proof would normally be calling some other source lemmas. Yeah. So how I can learn from this source theorem? If I'm given this source theorem, I should inspect what kind of lemmas it was using. So, and that was the idea. So, for example, I can't prove my specification that a tail recursive version of Fibonacci corresponds to recursive version of Fibonacci. Well, I have a look how it was done for factorial already. If that was the lemma that was suggested to me, well, someone else to prove that that theorem actually generalized that statement a little bit by adding an extra argument to it, because actually if you throw this fact to ACL2, it wouldn't be able to prove it. It needs an extra argument to help the recursion going. And of course, if I know that that's the method to prove that thing for factorial, I could pretty much analogize this auxiliarily helping lemma for my Fibonacci case. And that was the main idea there. So you have a look first at what's similar to your theorem, and then you look what kind of lemmas the suggested theorem was using, and then you analogize them, and then your proof goes through. So that was the idea. So Moore and Ewan were responsible for this part of analogy mapping. We're responsible for the statistical part. So I'll just tell you very briefly that there was a program, so it would gather here your source theorem, source lemma, and it would try to mutate somehow the term tree of the source lemma in such a way that it suits for your purposes. So very often it would be a new symbol that's going to be used in your new lemma. It would be roughly the same structure of the lemma, but yeah, symbols would need to be changed very often. For example, multiplication might need to be changed to addition, or a new argument needs to be added, such things. So, and that worked quite successfully as a domain-specific heuristic, because pretty much everything was very uniform in this library with the verification of GVM. So my feeling is that statistical methods will work anywhere. Anything that has to do with generation of new lemmas would work well in some domain where you know what kind of problems there are, and you can tailor statistics, heuristics appropriately. So this part is very much tuned to the particular library that we're using. So if we looked at what happened actually in this GVM example in terms of the clusters that we were getting, about 37% could be directly used by lemma analogy tool of Moore and Ewan to mutate lemmas. About 19% of clusters contain basic theorems whose proofs were just similar. 15 contain theorems that use the same lemmas in their proofs. 15 consisted of clusters that had theorems that were used as proofs in other theorems. And only about 14% of the clusters were actually such that we couldn't really see why on earth they were clustered together. But some good proportion of the clusters you see, you usually kind of see the similarity and reason why something was in the cluster. So that was recycling side, kind of not just clustering, revisiting the proofs, but also doing some kind of creative work on top of the clusters that you found. So, and very briefly about reusing of proofs. So there was a project, PhD project in Leicester by two people who are software engineers, not theorem proving people. But they somehow learned about Coq and thought that they may possibly help to automate some of proofs there. So I think the best paper that went out with them is CADE 25-1, Sepia search for proof using inferred automata. I'll show you just one picture to explain what roughly they have done. So imagine that you have a library, or imagine for a second that you just have one file with proofs. You can, of course, have a look at tactic applications, just at LTAC script, essentially, and have a look what kind of tactics are applied when. And then you can infer state automata from this. They used a little bit of machine learning on top of it in order to exclude the cases which are impossible. So some tactics are never applied after others. So these cases are excluded. I'm not sure if you could read it, and you probably don't want to read it, but it's quite a messy diagram. So it tells me that after the first step, so this is irrespective of any goal, yeah? This is what the library tells you what's happening generally. First step, second step, third step, kind of just those states of application of lemmas. Well, from this I could see that sometimes first step was induction and sometimes intra, and after that there was simplification or trivial or case and so on. So you can actually have a look at it and try to understand it. So I thought when I saw this, I thought, well, that's okay, why not? But the weakest part here was actually treating tactic arguments as constants. Yeah. So if your new proof also uses add NCA name for certain lemma, it will go through. But if you use a different name for the lemma, it wouldn't, because this thing would just retry all the tactics with arguments as they were present in the file from which you're learning. So I thought that was probably the weakest part of it, which our clustering tool was particularly good at, because it was able to look at the actual structure of all these arguments and go back and see what kind of lemmas they represent. So their accuracy, surprisingly, was not that bad. So this is their accuracy by just brute forcing, while doing a little bit of pruning of combinations of tactics that are completely impossible. But this is more or less brute force recombination of tactics on a few libraries. And I think it's just amazing how much they could get with just that. So apparently just brute forcing of tactics already works for some of the libraries. But you can see that, sometimes, especially in our GVM example, that was really relying on knowing exactly which auxiliary lemma you were using every time, because we replicated this from ACL2. This wasn't particularly efficient. I'm not sure what these 6 statements were, some random things that you were able to prove with OTA. But in some cases, they were surprisingly good. So I was actually surprised that it was that good when I saw this, bearing in mind that it was really abbreviated to what kind of tactic arguments they were. So I said, okay, so maybe how about we try to have, because I was all about this recurrent clustering, so maybe we'll be able to beat it with recurrent clustering. So my suggestion was to essentially try the ACL2 methodology. How about you just go back to your cluster and then only try to analogize your proofs from that cluster. Yeah. So I don't know, if I cannot prove a certain lemma max n ACA, I know you're too tired, so I won't ask you to understand particularly what the lemma says, but suppose that's my lemma, I cannot prove it. But I call M alpha PG, I see that it's clustered with some other 3 lemmas. And just as I was doing in ACL2, I'll say, well, let me analogize first of all tactics that were used in here, but also auxiliary lemmas. So in this particular case, one of the suggestions in the cluster had this proof. You see that the tactics are not particularly clever. I mean, the tactics could be anything. The really clever part is to know on which auxiliary lemmas to rewrite. So that was the kind of expert knowledge that you'd prefer to know. What do? I just take these clever parts, cluster them, find what kind of things are similar to these 2 little lemmas that were used. And indeed, I find 2 clusters that correspond to the first one and 2 clusters that correspond to the other one. And then just basically copy-paste the tactic combination, with the only difference that I put interesting auxiliary lemmas here that arise from clustering, rather than as people in Leicester were doing, they would just try to use this sequence of tactics verbatim in my new lemma, which in new lemma it wouldn't work, because the new lemma requires new auxiliary lemmas. So did it perform better, yes or no? And this is a comparison. And you see that in my GVM example that really relied on me having good auxiliary lemmas, I really was able to improve. Albeit here they were learning from, I don't know, 1,000 proofs or 50 proofs, and here I was learning this from 3 proofs given just by one cluster. So this was like a precise learning. Yeah, I was only learning from those lemmas, 4 lemmas that were 5 or whatever I was given, that were deemed to be similar. And this was learned from the whole of the library. So actually, when we went down, we didn't go down drastically. So 11% and 10%, this is very similar. But when we went up significantly because we were able to see the meaning of auxiliary lemmas and tactic arguments. So it looks like it's actually a question of a small proof. It looks like sometimes it's better to learn from a handful of proofs if they're right proofs than to write from a million of proofs if they're completely irrelevant to you. So this essentially was a relevance test. And this is how we came to conclusions. So the current work is really just to work a little bit on this slogan that we should data mine Coq types and proof terms, but generate LTAC tactics. Well, why is that? Because if I try to generate proof terms or types, generating these is extremely difficult. There is really an exponential explosion in how you can recombine different symbols in a proof tree. Or sorry, in a term or in a proof term or in a type. So generating proof terms is much harder than generating LTAC tactics because there are fewer tactics and fewer combinations of them to try. But data mining only tactics is somewhat silly because tactics do not actually express the content of the proof. Yeah, there are only whatever 20, 50 tactics there, and every time you apply a tactic, it has different semantics because its semantics depends on your goal. So seems like it's much easier to generate tactics, but it's much wiser to data mine types and proof terms, not in LTAC language. So, and I tried it on CompCert library to combine these two tools really, to have first clustering and then on top of this to have this automata generated proof trace as lesser people tried. Could I wait? It's almost the end. And it really we were able to discover about 188 new proofs on top of those found by SEPI before, and make some proofs shorter as well. So this brings me to the end of my talk, and question number 1, just as I told you, in my opinion there are few things that we could reasonably expect machines to do for us in the sense of statistical machine learning. They can find similar type proof structures and patterns beyond just notation. They can help to analogize lemmas and help to analogize proof reconstruction. But I'm still not sure if the community really wants to see much or little or at all of this kind of technology on the side of the user. So maybe the preference is for it to work like an ACL2 case when you just suddenly can prove more things and you don't know why this happens. Maybe the kind of interaction of which we were dreaming at the start is attractive. Maybe some combination. I think these questions is kind of important because there's going to be a new version of Proof General, and the question is whether to have a new version of ML4PG with its statistical recommender system in the new version. So this is me. There is one question.
Thank you. When you say that generating proof terms directly is unfeasible, can you say how many individual ways to construct proof terms there are?
It depends how many symbols you have in your library, and then it's an exponential. You're talking about exponential explosion. You're recombining all possible symbols in a proof tree, or yeah. Suppose we're talking about proof terms.
Right, but the methods by which you combine these symbols, that's...
We didn't, so the only place where we came close was this lemma, analogical lemma generation for ACL2. And there, if you narrow down all your symbols to just those appearing in your cluster, which means you only have 5 operations and maybe a few other symbols, so you're talking about 20 symbols to recombine. There it works okay, but even there's a problem that sometimes you need to analogize, you need to increase the number of arguments, so the branching of your tree needs to change, pruning or increasing. So if you have just a few symbols, it's okay to have heuristics that do it, but do it on a massive scale is, you know, taking all symbols of your library and somehow coming up with just correct proof term by recombination is extremely difficult. I don't believe in it.
Arnold and then Martin.
The success in this kind of method obviously depends on how you choose the features. So what is your method of choosing feature extraction?
Yeah, so I have a hidden piano in in the bushes. So so you want, when you design feature extraction, you want to be able, in principle, to have cases like this when this is append and this is plus, and you want to be able the tool to somehow abstract away from the fact, or rather see that append is actually itself defined similarly to plus. Yeah. So when you're trying to represent this as a vector, you want that vector to somehow bear the information that symbols that occur in your statement are also maybe pairwise similar, that this append is similar to this plus, which is not obvious. So this is a nice notation which makes it visually similar, but this is just add and this is just append if you desugar this to the actual definition. So you look at, this is as an example, at the tree that represents your statement. And at the first approximation, you think, well, I can always package this tree in a matrix because you need to somehow get features. So you get the first step of your feature extraction saying there is a matrix, and so this corner will always be the root of your tree, so every tree. So I want all of my proof trees or types that are represented as trees to be comparable in some way. So if the top node is there, I want to have it in the same place in the matrix for every term that I model, and so on. So basically, the matrix is just representing the topology of the tree. Yeah? So this is the depth, and this is the width of the tree. But the interesting part is how I actually, and then I need to populate this matrix with numbers. So I need to get rid of these for all symbols, and not, and so on. And this is a clever part. This is where this recurrent clustering kicks in. In order to assign a good number to for all, I need to see whether for all is in some sense similar to other symbols in the library. Well, for all is the predefined Galena symbol, so I can't do it for all predefined symbols. I say for all and exist should be assigned, say, same number or similar number. Say one is 1.1 and another 1.2. But I could go on and say, well, what not? Not is a defined symbol. I want to be able to cluster not with other symbols and with other definitions in the library, definition of not with other definitions in the library, and see to what kind of definitions it corresponds to, and assign close numbers to those definitions that are similar to not. You see what I mean? So it kind of goes, in order to extract features for this, I need to first cluster everything, all the library until those symbols that are used in my definition, cluster them, knows their proximity to other symbols in the library, and use my my number assignment according to whether not. So if not was similar to least definition, I want them not to be assigned 2.1 and least to be assigned 2.2, for example. So when at the end, when you provide those vectors then as numbers, the fact that I know not has some number actually reflects that it's similar to the definition of a list. So it goes recurrently. Anytime if I want to do this, I need to first cluster all these definitions, and if these definitions like even depends on some other definitions, I cluster them. So the clustering actually starts at the very base of the library and then goes up. This is in a hand-waving way. It's published.
Numerical values is done just on some heuristics, or is it tuned afterwards to get optimal performance on similarity?
We take the numbers of clusters and proximity values provided by machine learning algorithms in order to assign closer values, closer numbers to more similar things, and more distant values to dissimilar things. So that's how it goes. Yeah.
I actually have the same question, but if you have more hidden piano here, judging from your page count, then please show us more.
No, the rest is just what if you cluster SReflect library, what do you get as clusters? It was
And
like
then maybe rather take other questions.
Yeah, just that.
So I was wondering, do you have any feedback or experience with actual users? So I have people like using Coq downloaded, for example, ML4PG or any of those tools, and if yes, what was the feedback, and if no, what's the reason why it's not adopted, you think?
Yeah, not in a systematic way. We didn't advertise it too much to start with. We just used it, tried to submit, and we kind of were not sure whether it's something useful or kind of usable. Yeah, I think it's up to people trying. I think those people who tried it say that it was nice, but we didn't have any kind of HCI level. Oh, we asked 100 people to do this, and 60% said it was okay, or whatever. So we didn't do that.
So I have two questions. The first one is, how easy is it to disseminate this tool? As you are talking about using MATLAB, I don't know how easy it is for anybody to take it. And,
So MATLAB is not a good thing because you have to pay licenses and they're expensive. But there is Weka, so there were two tools we tried mostly. MATLAB and Weka. Weka is free. It's written in Java, but it's a free software. It's educational kind of software. So it was, the engineering side was very easy because those machine learning tools tend to run fast and they're convenient, and we actually, because it was prototype, we just implemented it as a bash script. It was calling the Java program from Weka.
Okay. There was a remark this morning by Tobias that for every definition there comes approximately 3 theorems. Could machine learning help know which are the 3 theorems for each definition? And because this is at another level of what we would like to have for machine learning, but this would be more like structuring the proofs, which is where some of our intelligence go. For people like George, for example, are very strong at that. And could we learn from that?
Yeah, well, in the same way you could see the clusters, and then if this is in the same cluster.
More like a suggestion.
Yeah. What the statistical method here does, it only just brings up the similarities based on kind of deeper analysis of the structures in the library, kind of taking into consideration all the recursive connections between different definitions.
Yeah.
So you're using recurrent clustering of the feature extraction. The thing that immediately strikes me is that this might actually be a nice way of indexing information for math information retrieval. Have you evaluated that? Because it would probably do well on similarity search.
Yeah. So so some of the hidden files just show what happens if you call this tool on the whole library. So I can give you a quick example. So we took the whole of SSHF file, or not whole, 7 files of it, and then we got 280 clusters, and then we had a look at them. So this was more to evaluate, does it make sense? Does the tool actually doing something that we're expecting? And some were homogeneous, that is, they were given patterns from the same library, and some were heterogeneous, they were going across libraries. And as an example, 36%, for example, were about some kind of related functions, like this would be a typical thing that it will show you in a cluster if you data mine the whole library. The cluster size is about 4 lemmas per cluster, so it's quite a small cluster. It's quite a precise thing for you to have a look at if you want. So obviously, take and drop are similar. This is something that you would expect to see.
I was more thinking if I gave you 300 million formulae that I mine out of the Cornell ePrint archive, what would you expect to see then?
Well, you probably hope to do something like this, I don't know. It's just you would have to tune your extraction algorithm, of course, from Coq files to the natural language. You're talking about libraries in natural language?
Yeah. natural language formulae.
Yeah.
But there's a word that uses the fact that we have lambda terms and that the things are done modulo alpha conversion. Would we be able to do a modulo alpha conversion on mathematical text?
Sure.
Yeah.
Well, probably try something like that.
Other questions? Okay, let's thank Katja one more time. We'll take a 5-minute break, but then do come back if you want to talk about the formal aspects.
Oh, yeah.